This is lesson 11 for quadrilaterals. A quadrilateral is a closed figure with 4 sides and 4 angles. The segments of a quadrilateral intersect only at their endpoints. So these are examples of quadrilaterals that each have 4 sides and they just have segments, and the segments only meet at the endpoints. So those are all examples of quadrilaterals. These are not quadrilaterals. This one has more than 4 sides. This one, these 2 segments meet somewhere other than their endpoints, and this one has a curved side that isn't a line segment. So those are examples of things that are not quadrilaterals. A quadrilateral can be separated into 2 triangles. And there's a couple ways you can do that, but if we wanted to separate this quadrilateral here into 2 triangles, one way we could do that would be to draw a line through it this way, and then you can see that there are 2 triangles formed. So the sum of the measures of the angles of a quadrilateral is, well, if there's 180 degrees in each triangle, it would be 2 times 180, or 360 degrees. So the sum of the measures of the angles in a quadrilateral is 360 degrees. So example 1 says find the value of x in the quadrilateral, then find each missing angle. Okay, well, we see 1, 2, 3, 4 angles that add up to 360 degrees. So we're just going to write an equation that shows that. Angle A plus B plus C plus D equals 360. So angle A plus angle B plus angle C plus angle D equals 360. Alright. We'll combine like terms on the left side. 3x and 4x is 7x. 90 and 30 is 220. And then we'll subtract 220 from both sides. So we have 7x equals 140. And then we will divide by 7. So we get x equals 20. That was part of the question. Find the value of x in the quadrilateral. We've done that. Then find each missing angle. Well, we don't need to find angle C or angle D because we knew the measures of those. We do need to find angle A, though. If angle A is 3x and x is 20, angle A is 3 times 20, which is 60. So this angle is 60 degrees. Similarly, angle B is 4x, and if x is 20, that's 4 times 20, which is 80. Okay. So there's a try it yourself problem at the bottom of this page, and you can pause the video, work through that problem. When you're ready to check your answer, press play. Okay, for this one you should get x is 25. And we have all 3 angles except for this one, which you should have gotten 75 degrees for. On the next page, let's look at classifying quadrilaterals. So we have just a basic quadrilateral at the beginning here. The only special property that has is that it has 4 sides. So from there, more specifically, a quadrilateral could be a trapezoid, which is a quadrilateral with exactly 1 pair of parallel sides, or it could also be a parallelogram, a quadrilateral with both pairs of opposite sides parallel and congruent. So these arrows here are showing the sides that are parallel. So here we have 1 pair of parallel sides and then a second pair of parallel sides, also showing that the sides are congruent. So a trapezoid really just has that one special property that exactly 1 pair of sides is parallel. In a parallelogram, both pairs of opposite sides are parallel and congruent. Well, a parallelogram could also be a rectangle, which has 4 right angles, or a rhombus, which has 4 congruent sides. Or, if it fits both of those properties, parallelogram could be a square. So you notice here you can say that a square is also a rhombus and a parallelogram and a rectangle and quadrilateral. So a rhombus is also a parallelogram. It's also a quadrilateral. It could be a square sometimes. A parallelogram is also a quadrilateral. So there's a lot of organization that goes on in these. There's not a single name that describes any single shape, but there's usually a name that best describes that shape, and that's what we'll be looking for in example 2. So classify the quadrilateral using the name that best describes it. Well, here I see two sides that are parallel. I see another two sides that are parallel. So I know at the very least, because I have two pairs of parallel sides, I know at the very least I'm dealing with a parallelogram. And I also notice that opposite sides are congruent, so that definitely fits the description of a parallelogram. However, beyond that, you see that all four sides are congruent, which means that this is more specifically not just a parallelogram, but a rhombus. Okay, so for the try it yourself, you're going to do the same thing. You want the most specific name to describe each of these figures. So go ahead and press pause, work through those four, and when you're ready to check your answers, press play. Okay, this one is a parallelogram. B is a rectangle. C is a trapezoid, because this side and this side appear to be parallel, and D is a square. Okay, that's it for lesson 11.4. Let's move on to lesson 11.5, polygons. A polygon is a simple closed figure formed by 3 or more line segments called sides. The sides intersect only at their endpoints, which are called vertices. Polygons can be classified by the number of sides they have, as shown in the table at the right. So in the previous sections, we've seen triangles and we've seen quadrilaterals. In this section, we're going to generalize to discuss any kind of polygon. So these are just some of the more common ones. Anything beyond 10, there's a couple other special names, but typically with those, we'll just use the number and then a dash and gone. So, and you'll see those later on in your notes. But these are the kind of more common ones that have those special names. So example 1 says to determine whether the figure is a polygon. If it is, classify the polygon. If it is not a polygon, explain why. Okay, so for the first one, I see something that's formed completely of sides. I see that the sides intersect only at their endpoints, or the vertices. So yes, this is a polygon. And to classify it, we just need to count the sides. We have 1, 2, 3, 4, 5. So 5 sides would be a pentagon. Alright, for B, I see some sides, however, I also see this right here. And this means that this is not a polygon. And it is not a polygon because it is not formed entirely by line segments. That curved side at the end here is not a line segment, so that means it's not a polygon. Okay, for the try it yourself, you're going to do the same thing. Determine if it's a polygon. If it is, classify it. If not, explain why. This one is a polygon. If you counted sides, there are 7 of them, which means that this is a heptagon. And this one is not a polygon for the same reason that B is not a polygon. It's not formed entirely by line segments. This is very clearly not a straight line segment. Okay, a diagonal is a line segment that joins two non-consecutive vertices in a polygon, forming triangles. An interior angle is an angle formed at the vertex of a polygon, or an angle inside a polygon. That's why it's called an interior angle. Okay, so basically why we need to know this information about a diagonal is you can take any polygon and you can draw all of the diagonals in from one vertex to each of the other non-consecutive vertices. And you will see that here, for example, I started with 6 sides and I drew all of the diagonals, and we're now left with 1, 2, 3, 4 triangles. And this will actually be the same no matter how many sides you start with. If a polygon has n sides, then n minus 2 triangles are formed. So if it had 8 sides, 6 triangles would be formed. If it had 11 sides, 9 triangles would be formed. If it had 20 sides, 18 triangles would be formed. So it'll always be the number of sides minus 2. So the sum of the degree measures of the interior angles of the polygon is n minus 2, the number of triangles, times 180 for each triangle. So this is the formula that will give us the sum of the measures of the interior angles of any polygon for whatever number of sides. So let's see how that works on example 2. Find the sum of the measures of the interior angles of a 13gon. So this is what I was talking about. We don't have a great name for something with 13 sides. We just call it a 13gon. Alright, well if it has 13 sides, I would subtract 2 to find the number of triangles that are formed when the diagonal is drawn from one vertex. So 13 minus 2 will give me 11 triangles formed, times 180 for each triangle. And 11 times 180 is 1,980 degrees. So if there's 13 sides, there are 13 angles, and all 13 angles together add up to 1,980 degrees. Okay. On the back, there's a try-it-yourself problem similar to this for you to do on your own. So pause the video, work through that problem, and when you're ready to continue, press play. Okay, for this one, the sum of the measures of the interior angles of a heptagon, you should have gotten 900 degrees. Okay, a regular polygon is a polygon that has all sides congruent and all angles congruent. I like to think of these as perfect polygons. They're the ones that you first learn when you're younger and you're first learning shapes. You always see, for example, you always see that perfect pentagon that has all 5 sides exactly the same. You always see a perfect hexagon, again, all 6 sides perfectly the same. A perfect octagon that looks just like a stop sign, all 8 sides exactly the same. And sometimes that causes a bit of confusion when you start to see shapes like, for example, let's go back. Shapes like on 1A, this is probably a regular pentagon, a nice perfect pentagon. But some of you might have been thrown off a little bit that we called this a heptagon when it clearly doesn't look like a nice, pretty 7-sided figure. So this name really just refers to how many sides there are. But if you're thinking of like a perfect heptagon or octagon or whatever it is, that would actually be a regular polygon. So this is more specific, a regular hexagon, a regular octagon. And that specifically is where all sides are congruent and all angles are congruent. So the name itself is general. When it's regular, it's referring to those specific properties. So for example 3, if I want to find the measure of one interior angle of regular 20gon, because we know it's regular, we know that all 20 angles are congruent. There's 20 sides, there's 20 angles. So if I can use the same steps to find the measures of all the angles combined, like we did in example 2, all I have to do is divide it by 20 to get the measure of each one, since they're all exactly the same. So let's start with that same method that we did in example 2. So the number of sides minus 2 times 180 to get the total measure of all of the interior angles. And when we subtract 2 and multiply by 180, we get a total of 3,240 degrees. But now this problem isn't asking for the sum, it's asking for one interior angle. And again, because there are 20 of them and it's regular, all 20 angles are congruent, so they split this evenly into 20 parts. So that's what we will do. 3240 divided by 20 will give us a measure of 162 degrees for each angle. So 20 angles in this polygon, and they each measure 162 degrees. Okay. I'm going to do the same thing on the two try-it-yourself problems, so pause the video and work through those two. Press play when you're ready to continue. Okay, for regular pentagon, you should have gotten a measure of 108 degrees, and for a regular 18gon, this should have given you a measure of 160 degrees. Okay. A repetitive pattern of polygons that fit together with no overlaps or holes is called a tessellation. The sum of the measures of the angles where the vertices meet in a tessellation is 360 degrees. And if you haven't seen tessellations before, I suggest that you just open a web browser and Google either tessellations or simple tessellations. And you'll see things like this. And some of these are much more complex than what we're really talking about in at this point in our class. But just as some examples of some really basic ones, like this, for example, you can see that you have a very basic hexagon shape, and you're able to completely fill, and you can imagine continuing on into space, you're able to completely fill the space just with that one shape repeated over and over again. Same thing with the triangles in this one. Again, you could fill this whole space and continuing on in every direction with these same triangles. Now, some of them used much more complicated shapes. Here we have an irregular quadrilateral that, again, will fill the whole space. But then you get some interesting artwork, even, with some of these other pictures. And this is what makes tessellations really neat, is that you get really, the more different you can create your pictures, the more interesting sort of results you get. Like here, you see that you have turtles, if you look at it one way, but then you have turtles going the other direction when you look at it. You can kind of see the turtles going both ways there. So the turtle itself is covering the entire plane. It's just repeated first in one direction and then in the other direction. But each of the turtle pieces fit together. We won't be looking at any of them that are complicated like this. We'll just be dealing with simple shapes like these with the parallelograms, or with these irregular quadrilaterals, triangles, etc. But that at least gives you an idea of a visual image of what a quadrilateral, or what a tessellation is. So let's head back over to our notes. Okay, so if we want to know, like in example 4, determine whether or not a tessellation can be created using each regular polygon, if we want to know, we just want to know, since all of the angles where the vertices meet have to have a sum of 360 degrees, we want to know if whatever angles we're dealing with in that particular shape would divide evenly into 360. So let's see what that looks like. So for a pentagon, for example, we actually already found the measure of each interior angle. It was up in Try It Yourself 3A. So part of this we've already done. Up here, we found that each angle is 108 degrees. So 108 degrees at each angle. Well, if I want to know if the sum of the measures of the angles where the vertices meet would be 360, if that were possible, I should be able to take 360 divided by 108, and it should give me a whole number. So if we divide 360 by 108, what we actually get is 3.3 repeating. This is not a whole number. So no, a tessellation could not be created using a regular pentagon. And why is that? Because 360 is not divisible by 108. Okay, let's do the same thing to see what we get for a quadrilateral. Now, we already know from lesson 11.4 that all of the angles in a quadrilateral add up to 360 degrees. But of course, if this was a different shape and we didn't know that, we would do the same methods we've seen prior to this example. So in this case, we would take 4 minus 2 to get the number of triangles, and then we'd take 2 times 180 to get 360 degrees. And if that quadrilateral is regular, that means that all 4 of the angles have equal measures. So this would be a rectangle, in which case each angle would be 90 degrees. That's 360 divided by 4. Well, it's probably pretty obvious at this point that this is going to go evenly into 360, since we divided 360 by 4 to get it. But just for the sake of example, we would divide 360 by 90 to get 4. And because this is a whole number, yes, you could make a tessellation from quadrilaterals. And we saw that in some of the pictures I pulled up on Google. Even irregular quadrilaterals, you can still make tessellations from those as well. Okay, so the last try it yourself problems, you can do the same thing. There's a few different steps involved, especially if they're ones that you don't immediately know the measures of the angles. So make sure that you find first the measures of all the interior angles combined, the sum, just like we did in example 2. And then don't forget to divide it by the number of angles like we did in example 3, so that you have the measure of just one angle. And then see if that number divides evenly into 360 to find out if you could actually create a tessellation with those figures. Alright, so pause the video, work through those two, and when you're ready to check your answers, press play. Okay. For this one, you should get 120 degrees at each angle. And then 360 divided by 120 is 3. So yes, you could create a tessellation there because this is a whole number. For a decagon, however, you should get 144 degrees at each angle. But then 360 divided by 144 is 2.5. And even though this isn't a repeating decimal like we got with the pentagon, still, this is not a whole number. There's no way for me to have 2.5 decagons at a particular intersection. So this would not be something that you could create a tessellation with. And why? Because 360 is not divisible by 144.